Imagine a star, dead but not completely gone. A star so dense that 1 cubic inch weighs as much as all of humanity. A neutron star is the bizarre remnant of a star that's gone through an explosive death, its core crushed into a nearly incomprehensible state, challenging everything we know about physics. But what really happens deep inside, what is hidden at the very core of a neutron star, we are about to embark on a journey into the heart of one of the universe's most enigmatic objects, exploring extreme conditions that could teach us more about the cosmos than we ever imagined. Neutron stars are remnants of massive stars that have ended their life in a supernova explosion. When these stars die, their cores collapse, creating an incredibly dense object, a neutron star. These stars are so dense that a single teaspoon of their material would weigh as much as Mount Everest. However, despite their mass, neutron stars are only about the size of a city, roughly 10 to 20 kilometers across. This extreme density leads to bizarre conditions, gravitational forces that distort time and space, surface gravity so strong that mountains can't rise higher than a millimeter, and magnetic fields millions of times stronger than the Earth's. Neutron stars aren't just dead remnants, they are active physics laboratories. The conditions inside these stars push the limits of matter, challenging our understanding of physics itself. At the core of a neutron star, the material is under such extreme pressure that regular atomic matter is crushed and transformed into forms that don't exist anywhere else in the universe. Physicists call this process degeneracy pressure, an invisible force that prevents the star from collapsing further, keeping it at the precipice of oblivion. What makes these objects so fascinating is how they force physics to go to extremes. Inside the heart of a neutron star, quantum mechanics and general relativity, two pillars of modern physics, collide. For example, the concept of degeneracy pressure, which was first theorized in the context of white dwarfs by Ralph Fowler, is what prevents neutron stars from collapsing into black holes. This pressure is the result of quantum mechanical principles that govern the behavior of particles, specifically the Pauli exclusion principle, which dictates that no two particles can occupy the same state. The story of neutron stars is not just one of astronomical curiosity, it is interwoven with historical discoveries. Take, for example, Maggnad Saha, whose research in the early 20th century led to the understanding of how the sun, and by extension, stars like it, are structured. Saha's ionization equation helped us understand how stars burn and how their cores are composed. Without this framework, we wouldn't be able to make sense of the extreme conditions in neutron stars. Similarly, the work of Subrahmanyan Chandrasekhar on the mass limits of white dwarfs laid the foundation for our understanding of how the massive stars transform into neutron stars. It's through their discoveries and contributions that we begin to appreciate the beauty of these cosmic objects and the delicate balance they maintain between the forces of gravity and quantum mechanics. So, what exactly is in the core of a neutron star? It turns out that the deeper we look, the more questions arise. One of the most recent mysteries came from a neutron star named J0740. This star, discovered through data from the NICER telescope, is surprisingly large for its mass, challenging our predictions about how neutron stars behave under pressure. This discovery forced scientists to rethink the equation of state, the fundamental relationship between the pressure, density, and temperature of the star's interior. What makes J0740 so puzzling? According to current models, the more mass a neutron star has, the smaller it should be. However, J0740 defied this expectation, suggesting that the interior of neutron stars might not be as squishy as we thought. This discrepancy could be due to the presence of new forms of matter, such as hyperons or even dark matter. When we think of the core of a neutron star, we typically imagine a mass of neutrons packed tightly together, forming a dense, degenerate core. But what if this isn't the full story? What if, deeper still, there are other exotic forms of matter? One theory proposes that as the pressure in a neutron star increases, the neutrons themselves might break apart, creating a soup of quarks, fundamental particles that make up protons and neutrons. Some scientists even suggest that this quark soup might give rise to strange quarks, leading to the formation of strange stars. These objects would behave very differently from traditional neutron stars and could explain some of the mysteries we see in stars like Ju 740. The theory of neutron stars and their mysterious cores has not just remained in the realm of textbooks and equations. In fact, it has had a real-world impact in shaping our understanding of the universe. One of the most significant events came in 2017 when two neutron stars collided, producing both gravitational waves and light. This event, known as GW provided astronomers with a unique opportunity to study the extreme physics of neutron stars in action. Using the data from this collision, scientists were able to refine their understanding of the mass and size of neutron stars and narrow down the limits of the TOV limit, the maximum mass a neutron star can have before collapsing into a black hole. This breakthrough could help answer some of the fundamental questions about the nature of these stars and their cores. The mystery of neutron stars isn't just about understanding their structure, it's about understanding the universe at a deeper level. These objects are some of the most extreme environments we can study, and by exploring them, we might finally be able to reconcile some of the biggest mysteries in physics. Could dark matter be part of the equation? Could quantum mechanics and general relativity coexist in a unified theory? As we delve deeper into the nature of neutron stars, we may uncover a new kind of matter, one that might change our understanding of space and time itself. The future of neutron star research is wide open, and each discovery brings us closer to answering the ultimate question: what truly lies at the heart of a neutron star? In conclusion, neutron stars are far more than just remnants of dead stars. They are the universe's ultimate physics experiment, offering a glimpse into the extremes of matter, energy, and gravity. As we continue to study them, we may not only learn more about these enigmatic objects, but also about the fundamental nature of reality itself. The journey to understand the core of a neutron star is still ongoing, and the discoveries we make along the way will have profound implications for the future of astrophysics. For now, though, the mystery remains unsolved, and the heart of the neutron star continues to be one of the universe's greatest enigmas.